Well, thank you for this kind introduction, and also kind invitation to come to this wonderful event. So it's a great pleasure to be here again, the second time, at the second ICBS conference. So I slightly changed the title, and I'm going to try to talk about higher symmetries, first from quantum field theory perspective, and discuss some more recent developments that address the symmetries by introducing the so-called symmetry theories. And so the major point in this talk will be to discuss actually how the symmetry theories that determine higher symmetries in quantum field theories can be more complex, nested into each other. So this is a work that should have been out, but should appear anytime now. And it's together with Ron Donaghy, Jonathan Heckman, Max Hübner, soon to be Curie Fellow at Uppsala, and Ethan Torres, the fellow at CERN. This is part of the Penn Group effort, and some of the things I'm going to talk about will be also based on earlier related works, also with Jonathan, Max, Ethan, and also Hao Zhang, who is at IPMU now in Tokyo. So the way we typically address higher formal symmetries in quantum field theory, I may need a pointer. Yeah. Just need the pointer. I'm so sorry. Can you disable this part? In any case, yeah, let's go ahead. You see, this is okay. Okay, so let's start again. One way of introducing higher form symmetry is to introduce non-dynamic extended defects in the quantum field theory and related symmetry operators that act on these defects. So an example of 3+1 quantum field theory with one form symmetry would involve introduction of a string and a corresponding closed loop symmetry operator that acts on it. Similarly, the standard zero form symmetry and the global gauge transformation on it are, of course, the standard parts. So when we are talking about higher form symmetries, we are going to one, possibly more complicated symmetries. In particular, when we have one form symmetries that non-trivially intertwined with zero form symmetries, it turns out that the symmetry structure of the theory is more complex, and it leads to the so-called two-group structure. So on a related side, higher form symmetries in quantum field theory have been recently studied by introduction of the so-called symmetry theories in one dimension higher. And it's the symmetry theory that captures this higher, more complex symmetry structure of resulting quantum field theories. This turned out to be, right now, an active field of research. And what I want to point out here is some more involved new perspective in the study of symmetry theories. In particular, what I was already alluding to, the nesting of symmetry theories in order to address more complex global symmetry structures of quantum field theories. And in the second part, I want to actually elucidate how this nesting of symmetry theories naturally appears in string theory via geometric engineering. So let's start with a basic motivation for studying global symmetries in quantum field theories via symmetry theories. So the idea is that we start with the given quantum field theory, say in D dimension, and when we try to study its symmetry structures, we can often isolate the symmetry structures in a topological field theory in one dimension higher. This led to the introduction of so-called symmetry topological field theories in one dimension higher. So pictorially, we start with quantum field theory in D dimensions, and then we extend it in one dimension higher by symmetry topological field theory, where now the original quantum field theory in D dimension is associated with the physical boundary conditions on one side of this one dimension higher field theory, and on another side, we are dealing with topologically boundary conditions of the symmetry TFT that then gave us information on higher symmetry global symmetry structures. It turns out that many symmetry structures depend only on the topological boundary conditions of a symmetry TFT. Now let's go on and look at this symmetry TFT in isolation by itself. So we remove the boundary conditions, so without edge modes, and this is now looked at not in the context of initial lower dimension quantum field theory. Well, such symmetry TFT is actually now just quantum field theory in one dimension higher. It turns out that it's particularly natural to take this perspective and in the context of studying continuous global symmetries, where the symmetry TFT is not necessarily topological field theory anymore. And it's now replaced just by symmetry theory. Yes. Well, I'm not sure, maybe, yeah, so for the case of global continuous symmetry, yeah. Yeah, but Jonathan wanted to comment, yeah. Because it's a global at the end, right? You're addressing the global symmetry structure. So it's, yeah, in that sense. Yeah, okay. Basically introduced by groups in our broader community. In any case, in general, we would view that now as a more non-topological symmetry theory, okay? And now, you know, we go to the next step, take this symmetry theory, and we have returned to the starting point. It's just QFT of certain type, effectively. So we can reiterate the procedure and talk about construction of symmetry theory in another dimension higher. Okay? So let me pictorially sketch this. So we are starting with symmetry theory in D+1 dimension, okay? And we now decompress it to study further its further symmetry structure into symmetry theory in one dimension higher. So that's without boundary conditions. Now let's recall that the symmetry theory was introduced in one dimension lower, and we add the physical boundary condition here. Now, this decompression of symmetry theory in D+1 dimension, in D+2 dimension, takes now this boundary condition, physical edge modes, into the edge modes that that is connected now to two D+1 dimension symmetry theories via D+2 symmetry. So returning back to what we came from, we naturally now see the origin of this physical edge modes in original field theory as modes that connect two symmetry theories in one dimension higher via symmetry theory in dimension D+2. So this nesting idea can be actually extended, and it could in principle continue. So this is sort of like foundational introduction of this nesting symmetry theories. Now, there is actually additional motivation for nesting of symmetry theories. And this is via introduction of defect quantum field theories in original say we have original capital D dimensional quantum field theory, and we insert into it the defect quantum field theory in smaller dimensions than capital D. And the question you would want to ask yourself in this context is, what is the symmetry theory of the combined system? So, via symmetry theories, right, we see originally we have D-dimensional quantum field theory, and we insert the quantum field theory of the defect. Now we construct the so-called sandwich, namely we have a capital D+1 symmetry theory in principle that is associated with the original quantum field theory, but now there is also the defect, and it's associated one dimension higher symmetry theory. So typically, it's natural to compactify a D minus, compactify these directions in the bigger quantum field theory to just one dimension higher than the dimension of the field theory of the defect. So this physical corner mode here, that is part now of the Kaluza-Klein reduced original physical theory, is now accompanied on one side via symmetry theory in its one dimension higher, and then that connects, right, to the original field theory, Kaluza-Klein reduced, and its associated one dimension higher symmetry theory. And this picture is actually the same I drew earlier, just a little bit rotating and deforming the previous example. So actually thinking of defects within original quantum field theory naturally leads us to the introduction of this nested symmetry theories and the corresponding physical edge mode sitting at this corner. All right. So this was from the field theory perspective. Now let's go to the string theory interpretation of this phenomenon. So these higher global symmetries naturally have geometric engineering interpretation, namely interpretation from string theory. So we are talking about resulting quantum field theory with defects and symmetry operators, and the way we obtain this field theory is by compactifying string theory on non-local, on non-compact space, typically non-compact Calabi-Yau space, okay? And this is an example when we compactify it on conical non-compact space. So this is an example of what we would call prototype example of isolated singularities. So the quantum field theory in the resulting space-time is associated with the singularity at the bottom of this cone. Now, the interpretation of defects in this picture is associated with defects being generated via branes wrapping this relative non-compact cycles that extend all the way to the boundary. Analogously, the symmetry operators associated with this defect are also associated with branes, but those are branes that wrap cycles on the boundary of this non-compact conical Calabi-Yau space. So if we take M theory, the defect operators and symmetry operators are now associated with M2 branes or M5 branes wrapping the non-compact relative cycles or compact ones on the boundary for defects and symmetry operators respectively. And this can be quantified as determining the features of the resulting defect group in terms of this relative homologies associated with these non-compact cycles, and similarly also with the corresponding symmetry operators as corresponding homology on the boundary itself. Primarily in the discussion of geometric engineering, I will focus really on M theory per se, and I will take electrical defect associated, namely with M2 branes and producing one-form symmetries and the defects in the resulting theory. Okay. Now let me turn back to the symmetry theory interpretation of within string theory. So emergence of symmetry theories in string theory is also just natural and on the nose in this case, as this extra non-compact conical space naturally provides extra non-compact radial direction on which we construct the corresponding symmetry theory. So here, on one end, we are dealing with the physical topological conditions associated with the original resulting field theory, and on the other end, boundary, we are dealing with the topological boundary conditions, and we can deduce the higher symmetry structure by understanding the resulting symmetry theory here. So this is the simplest, this is analog of 1A. Now, how about nesting? Actually, string theory again provides plenty of examples where we are dealing with general nestings. Okay? Namely, what in the picture when we relate this nesting with the defects inside bigger quantum field theory, this comes very natural interpretation in this case. So let me just highlight a prototype example. So what we are dealing here now is with non-isolated singularities. Okay? And this is well-beloved example of intersecting flavor branes on non-compact space. So if we are talking about flavor branes, because they wrap this non-compact cycles, they intersect in the interior and produce the defect degrees of freedom at this intersection. Famous, typically in type 2A, this is the famous massless fermion in the freedom. So we can use this tubular excisions to interpret now this configuration back in constructing the resulting symmetry theories. So let me go to that. Okay. And basically, as I said, this is very natural. We have a defect inside bigger symmetry, bigger flavor theory of intersecting branes. And so in this case, now we can really connect this geometry that we have to the symmetry, interpret this geometry and deduce the symmetry theory of this full system of flavor branes and the defect and intersection and construct resulting symmetry theories that arise from there. So geometrically, again, with these excisions, we have the defect, we have the intersecting branes. Those are the tubular excised regions that we introduce. And this can now be interpreted in the symmetry theory, nesting of symmetry theories, in the way that the defect that is at this intersection becomes now the edge mode of this defect theory. And above it, we geometrically construct from geometry the resulting symmetry theory in one dimension higher. Now, with this compactification of flavor branes down to just one extra word volume dimension, we are dealing now with the physical boundary conditions in the resulting flavor brane field theory. And above it, we geometrically construct the symmetry theory in one dimension higher. Again, this edge mode is actually sitting there as a corner mode, right, between the brane field theory that extends into this nested one dimension higher symmetry theory and its corresponding symmetry theory of the original defect. Anyway, one can quantify all that, but here we geometrically, we see this phenomenon happening very naturally. So in the rest of my talk, I want to maybe quantify a bit more example where this nesting of symmetry theory produces really new physical insights. Okay. So I will just focus on one example where I do a little bit more details in constructing nesting field theory, and then I make some pose some outlook and some concluding remarks. I think the way I'm going, I will not have much time to talk about defects when we compactified string theory and studied the fate of the symmetries also within new perspective of symmetry theories. Okay, so the prototype examples where we would explicitly study this interplay nesting of symmetry theories will be an example of non-compact orbifold in M theory that is not only associated with CFT at the bottom of the cone, but it also has now a flavor brane itself. So at codimension 3, we have the singularity associated with SUN gate symmetry in the resulting field theory. And then we are having also flavor brane wrapping this non-compact codimension 1, codimension, codimension 1 example where we are dealing now with this flavor brane extended all the way to infinity on non-compact cycle and is associated with SU2 symmetry. There is analogous interpretation of this geometry via fibration over the Z3 complex coordinate. So again, this defect picture is very natural here. So we are dealing in resulting theory with SUN, superconformal field theory, and which is now viewed, this defect is now viewed as this 5-dimensional CFT is now viewed as defect within 7-dimensional SU2 flavor symmetry. Actually, you know, we studied those orbifolds more directly by using hands-on algebraic topology techniques. What we done is we were cutting and gluing singularities on the boundary of these orbifolds and employ Meyer-Vietoris sequences to determine what is the actually genuine one-form symmetry, torsional Z2 symmetry, and whether there is some interplay there. So this generically, these orbifolds with flavor branes inside, right, have the flavor branes extended to the boundary, producing additional singularities that we cut and glued back. And using Meyer-Vietoris exact sequences, we were able to, with some physical intuition, determine the sequences that identify the group elements of one-form symmetries and the torsional Z0 form symmetries. In particular, in the sequence, the true one-form symmetry that is associated with the singular boundary space sits here, and the true flavor symmetry sits in this sequence as a kernel. Using some orbifold homology calculations, we were able to actually determine for all these different orbifolds what the true one-form symmetry is and corresponding true flavor center symmetry is. A particular thing that we notice is in non-trivial cases like this one that we have, actually, this is for our case, this result, it turns out that when this sequence doesn't trivially split, when this is not just the sum of those things, and this is the case here as well, okay, we see that actually there is now, we can go cut this, compress, and see the intertwining of true flavors center symmetries with true one-form symmetries, which leads to the two group structures in this context. And beyond this non-compact orbifolds, we also got examples of this one-form symmetries and two group structures in other examples like elliptically fiber Calabi-Yau's G2 manifolds and so on. But this is not so much the point of things I'm talking about here. I want to take now the perspective of constructing the corresponding nested symmetry theories in this 5D, 7D, 5D defect in 7D flavor field theory. Well, you would ask me, but you've already done that with some other techniques. Why is that any better? Okay. The point is we understand more structure, actually the Lagrangian terms, the anomaly terms that appear in this construction by identifying symmetry theory in more details in this context. And furthermore, okay, it's not necessarily done just by for the one-form topological operators. It can be done also for all the other possible operators. And we could study more physically here how topological, more general topological operators behave when we push them from the bulk symmetry theory to the boundary defect symmetry. In any case, justifying that, I will still go back to one-form symmetry and see how we interpret now this nested field theory, symmetry theory in this context, and how we actually obtain the same result about the one-form symmetry and the two-group structure. Anyway, so the idea is, as I said, I argued already, that we are dealing now effectively with 7D flavor theory and the corresponding defect of 5D superconformal field theory. We can actually, one dimension is not that relevant in this process, so we can compactify one dimension in the system. This would be associated now with the word volume of flavor branes. but not the radial direction. And we obtain effectively from the flavor brane 6D field theory, and there is a corner here, the defect, okay, associated with 5D superconformal field theory. So the way we construct now symmetry theories is from normal geometry, both to this flavor branes and the superconformal field theory, via reduction of 11-dimensional supergravity. Okay? In particular, topological terms of 11-dimensional supergravity. And in this reduction, of course, we do that on corresponding leftover radial slices. So this produces for us now the resulting 7-dimensional symmetry theory of the flavor branes and the corresponding 6-dimensional symmetry theory of the 5D conformal field theory and physical edge modes on this corner. So what can we do with this interpretation? Okay. Particularly, I can focus now on understanding how one-form symmetry is associated with 7-dimensional symmetry theory of the flavor branes, okay, is fixed by the boundary conditions of the 6-dimensional superconformal field theory symmetry. So, oops. Okay. So I'm going to focus in particularly how these boundary conditions with this bulk symmetry theory and boundary field theory of this defect, okay, are intertwined and actually determine what are the allowed true symmetries of this conformal field theory. So I'm focusing only, there's more to the story, but let me focus just on one-form symmetry backgrounds in this context. And so they are the source for 6-dimensional flavor branes by 2 cycles, torsional 2 cycles associated with Z2 in the symmetry, 7-dimensional symmetry theory, and the corresponding one-form symmetries of the CFT that in its corresponding symmetry theory is associated by via torsional 2 co-cycles of Z2N structure. And again, this is all obtained by doing this M theory reduction, in this case of the 3 form of F theory down to this symmetry theories and obtaining this corresponding 2 co-cycles that source one-form symmetry in the branes and one-form symmetry in the conformal field theory. And now there is a boundary condition in this nested theory. And so at the boundary of the 7-dimensional brane, flavor brane symmetry theory, on the end, we have to relate this 2 cycles to the 2 cycles of the corresponding CFT symmetry theory. And we end up with N conditions here. And so what we end up, instead of naively thinking that we are dealing with Z2N, one-form symmetry, we have really profiles only of N one-form symmetries that still survive. So it's this boundary condition associated with this pushing bulk symmetry theory, the boundary, and that fixes for us really the true one-form symmetry of the theory. Okay, so this is basically the hallmark, this non-trivial boundary conditions produced in this nested field theory context for us, a non-trivial interpretation of one-form symmetries, and as a consequence, actually, such non-trivial boundary conditions that further restrict the true one-form symmetries are typically hallmarks of appearing of the two-group symmetry in this context. So I'm reproducing the same results, but really with physics on, with real fields, with real topological field theory here. In any case, we have now both, with this bulk boundary symmetry theories both field theory interpretation, what has happened due to this boundary condition, and we have also geometric interpretation, which is corresponding cohomology calculations. In any case, so I hope I gave you some flavors of how nested symmetry field theories in general are important in understanding more complex symmetry structures of quantum field theories, and how string theory actually is a natural framework to address those things. Okay? Because the geometry translates for us really, through also having 11-dimensional supergravity theory and topological terms there, really to constructing the resulting bulk and boundary symmetry theories there. Okay. I would probably like to highlight still maybe a few other things that we observed, and we are still grappling with technical details here. In particular, we can now address, since we have Lagrangian, that we reduce symmetry theory Lagrangian, that we deduce from M theory compactification, the corresponding anomaly couplings appear in the symmetry theories. And we found now new type of anomaly couplings in this context that actually are related now to mixed anomalies of flavor one-form symmetries and that of the corresponding conformal field theory. So that would be associated with the corresponding one-form ones in the CFT and the corresponding flavor ones. And these anomaly terms are forced to be rational, to map into rational numbers of specific kind. Okay? And furthermore, we also see the pure one-form self-anomaly associated with just superconformal field theory one-forms. And that also has specific map into rational numbers that we further have to quantify and really determine that this is the case. So I could have possibly ended my talk here. So clearly, there are lots of things that are still work in progress. We have to refine calculation of mixed anomalies now between flavor and the real CFT one forms. As I said, this is work in progress, and that's why we need mathematicians to be involved in that. There are more examples also in the upcoming papers. There is possibilities of higher order nesting, so this opens possibilities both from field theory and from string theory, geometric engineering to address this higher form nesting in the resulting symmetry theories. I would maybe like to highlight one thing that we are also pointing out, that what we saw is this certain symmetry inheritance that we obtain from bulk symmetry theories and what happens due to boundary conditions as we go to the boundary field theory, symmetry theories. And can we relate now how these defects are related to each other between bulk and boundary CMT picture, and to quantify this in and understand better in more examples. Okay. And that's one particular example that is somewhat intriguing, which is actually talking about lower form symmetries. I talked about higher form symmetries, one form, two group, and so on. Okay. So lower form symmetries actually appear, let's say, in the bigger quantum field theory, if we have so if we are dealing with the bigger quantum field theory, there is naturally way not writing just zero form symmetry, which is a point, but now also one form symmetry, whose one form symmetry fills operators just fill out the whole quantum field theory space time. So it's the space-time filling operator. So there is one form symmetry in this bigger quantum field theory, and now we zero on to the defect in it, and it can be naturally viewed that there's one form symmetry when constrained to the defect field theory would naturally allow us to deal with even lower form symmetries. You know, it is bound depending on what is the dimension of the defect field theory. Okay. Well, this is just really the idea, and one would really have to quantify this phenomenon better. Is it really possible, and how it's possible to get even very large negative valued form symmetries? And in particular, is there bound? It's also how does boundary conditions work and how this is properly viewed in full-fledged symmetry theory analysis. So it's somewhat open question. Okay. So in the outlook, you know, there is the last topic I was alluding to, but I don't think it's the least topic. Okay. Because we definitely want to understand what happens to hard form symmetries in compact models. Okay. And that is, again, a part of the swamplet program, but really to understand the whole picture when we couple really quantum field theories also to consistent quantum gravities, what happens to hard form symmetries, or how can we trace its origin or its behavior as we compactify the theory. So this is, of course, subject close to my heart in general, but to address it within hard form symmetries, the subject is really rather novel. There was some progress already that took place in the past few years. There is a general mantra that global symmetries in consistent theory of gravities, including hard form symmetries, should either be gauged or broken, and that was specifically addressed for hard form symmetries by Harlow. In A dimensions, actually, with the work together with Marcus Dirigal, Ling Lin, and Hao Zhang, we addressed the issue of gauging of one form symmetries, actually in very high dimensions. And we quantified their conditions that the one form symmetry can be gauged if there are no specific anomalies there, and we quantify this particular anomalies there. And that actually led to study of broad classes of A-dimensional string compactification, actually some beyond F theory, by also using refined string junction conjecture, and still current work to address also frozen singularities in this context, that of course are all compatible with this specific no anomalies condition for gauge one form symmetry there. Well, this is sort of some parallel work, but I want to bring this picture here now in the context of gluing the non-compact spaces I talked about, and also talking about how to proceed with constructing corresponding symmetry theories in this context as we compactify them. So with all most of the talk, well, all the talk so far was studying really only non-compact examples, quantum field theories, non-trivial brain configurations, nested symmetry theories constructed from there. Okay. But now what we want to take is, we want to take these non-compact spaces and glue them into compact ones. And interpretation is the field theories we were dealing with will now result in some final consistent quantum field theory that also includes gravity. Okay. So schematically, we were dealing with this non-compact conical examples. So this is with just one singularity at the bottom of the each conical, non-compact conical space, and the corresponding defect operators that are related to branes wrapping these non-compact cycles. So we have these non-compact cases, and now these non-compact cycles associated with each non-compact geometry has to be glued together consistently, okay? And so particular defect that we have in non-compact case, and it was allowed, okay, can either not be glued into consistent compact cycles in this case. That would mean that this defect that we construct in non-compact case actually does not survive compactification. Symmetry is broken. Now, the cycles can actually, non-compact can, in some cases, be consistently glued. And what this gives us is now compact cycles. That means we are dealing with the flavor branes that become dynamical, compact, and we are dealing with really now physical degrees of freedom appearing. From the perspective of symmetry operators, which live on the boundaries, what happens in this case, they are identified and the symmetry is trivialized. So this is the simplest picture. Of course, we want to go to the nested picture of this gluing condition. But corresponding, so this is just saying what I was saying in words, right? When this relative cycles survive the gluing, okay, we are dealing actually with, they become dynamically engaged, right? Yes. Yes. Oh, well, we still have to glue them, right? So let's say I cannot, this is sort of like a dual picture of the defect, right? So let's say that I cannot glue defects, okay? So I'm dealing now with symmetry operators just sitting there, not being identified. Well, yeah, but the question that I ask is, you know, how do you glue it? What happens, right, when you cannot glue cycles into compact ones of the defects? Yeah. Yeah, it's broken. Yeah. Indeed. So you would say here it could become topological. No, it could become dynamical in principle, right? Since it's not trivialized, maybe the gluing still. And actually, in higher dimensions, we see this duality, actually, right? It's coming back. But yeah, it could be. But let me not, yeah, it's again, very important question. In any case, for the case, you see, when we are dealing that on just 4-dimensional spaces like K3, okay, this can be done explicitly and completely, okay? And again, in earlier work, we studied this phase again via cutting and gluing. The same ideas and quantified again via Meyer-Vietoris's long exact sequences, okay, that would relate now how homologies of the compact space are related to the part without local ones. So this is analog of this, a regular part in the absence, so compact space and taking away the local parts. And so this relating now x zeros to x and the boundaries allowed us to construct now the interpretation of one form symmetry, say, and the corresponding, which would be associated then with the corresponding cycles, and tracing what happens both to defect operators and the symmetry operators. Well, the sequence turns out to be short one in the example of four-dimensional spaces. For example, T4 orbifolds or K3 surfaces in general allow us to truncate this sequence to a finite one. And that may be, here are issues of interpretation of symmetry operators and defect operators in this context. Okay, and so I'll just say it in more qualitative words. So identifying H2 of the compact space tells us the number of compact cycles. This is where the defect has been actually become massive, right? And correspondingly, we have physical matter associated with that, okay? But then, because defect and symmetry operators actually in that low dimensions are associated with the same type of homology, okay? In the local case, okay, we can trace what are the original local model defect and symmetry operators here, okay? So this element basically tells us what happens to the defect on one side, right? Whether it's massive, the cycle survives, so it's being gauged and it's finite, trivializing symmetry. But there is also, as Jonathan said, there's a dual way of viewing that also as taking this symmetry operators as well and see whether they are trivialized. That's when the gauging happens for the defects, okay, or correspondingly, if it's broken, we can also see that we may get also a finite size symmetry operators, which are not symmetry operators. In any case, right. So in principle, this is the part here where we can trace what happens, gauged or broken, and this is the local picture. And so that allowed us actually to construct the sequences for orbifolds. Thank goodness to excellent postdocs who carried out these calculations, and also for some non-compact ones, so we can trace what happens to H2 here. And as a byproduct, we actually get the complete information about the full gauge group in these cases, which also has not been done before. So, and there's some other subtleties. We can trace also the appearance of U1s, which are non-topological here, basically, and global effects. In any case, the story can be done here, but this has to do really with the case because the non-compact models all had only localized singularities. And this analysis, you know, can be done explicitly. As we go to higher dimensions, like higher dimensional, 6-dimensional compact orbifolds, there we are dealing now with another stratum, codimension, lower codimension singularity associated now with the flavor brains, okay, which we don't have in T4. T4 is trivial, just a single localized singularity for each non-compact models. And that's technically hard. We managed to handle that in some very specialized cases, okay, for Z3 orbifolds. And there, the symmetry, oops. Oh yeah, the symmetry operators and the defect operators are not sitting with the same homology groups. They are not. So we are dealing with two separate spectral sequences, and we can trace what happens to these things from these two sets of spectral sequences. But due to the lack of the time, or maybe I should point out You see, this is associated now with symmetry operators. They are not, and there's comparable thing where we are tracing effect operators there. We also see whether we gauge or trivialize symmetries. This is associated with those maps. And also, you know, compact spaces, we add matter when we gauge symmetry. So we can trace in this sequence concretely how the symmetries are being either gauged or broken, both for the for the defect operators, but then we have this analogous symmetry operator sequences as well. And as a byproduct, of course, get the whole concrete global gauge group structure. But let me turn, this is the last point. This is gluing and cutting and using the corresponding exact sequences to identify what are the surviving cycles or surviving what happens actually to higher form one form symmetry specifically here under compactification. And so, of course, in all these examples, we concretely verify either it's broken, it's not there, or if it's there, it's really gauge symmetry. And we want to really address more concretely those issues now from the perspective of symmetry theories as well. Okay? And so this is now the simplest example where we have singularity at the bottom of these non-compact cones, and we are gluing them together. Recall that in this case, the symmetry theory is naturally associated with this radial slicing here, where at the bottom we are having the physical boundary conditions, and then we are going now to the interior of this non-compact space, a compact space. Okay, and so we can view that now a symmetry theory is associated with each non-compact example, and now in the center they are being glued together, they come together. And so in the center we have now typically some boundary conditions that are not completely topological. For example, U1s are not in this construction. So these boundary conditions are typically not completely topological, but the interpretation of these underlying symmetry theories together with these junctions is what was referred to as symmetry trees. And that's the simplest example of that type when we only are dealing with isolated singularities in non-compact cases. This has been addressed already, but also by some of the subsequent work. But the really hard thing in view of nesting of symmetries, right, and nesting of symmetry theories, we really want to include now flavor brains in this context, which appears, for example, in 46 examples, of course. And there we are dealing now with new strata of singularities. And we want to systematize actually this gluing procedure better that would lead now to nested symmetry trees as well. As I said, from gluing and cutting using topological algebraic topology, we got some very special examples, but we don't have systematic way of doing it. So at least to get complete understanding of these things, the compactification of 6-dimensional spaces, I think would be a very important thing. Because basically we understand all that for 4-dimensional space. They're really to a large extent. In any case, so there's plenty of work to continue, and I would like to thank you for your attention. Oops. Oh. Sorry, what is
on the for symmetry theory for 5D ICSP from anterior non-isolated arc. How do you actually do that? Do you do some kind of different action reduced on this excited line?
Exactly. It is okay. You use M theory, right? And then you reduce it along this radial slices on geometry transfers, safe to the flavor brain. Okay. Particular one, since I'm not doing the full Lagrangian now, right? I'm doing, I want to identify the field that sources one form symmetry in this context, right? And I said that's how we found them, and we can find how many of them we had, subject to what discrete symmetry properties, okay? Now from the boundary, which is conformal filter, you do the same thing. And you see that many one form sources there. The thing is, as the bulk symmetry goes to boundary, these things are connected. And that's where we get from symmetry theory, these boundary conditions. But it comes from originally doing this co-cycles in the bulk and the boundary from M theory reduction. Maybe I haven't asked, yeah, because I think you're talking probably about the full Lagrangian. Right. Higher symmetry, sorry, flavor symmetry, yeah. Well, from geometry, you sort of know because you're doing reduction from the geometry transfers to this flavor brain. You see, you reduce M theory, right? You do, and slicing, and along the slicing, right? This is what gives you. So you can do that directly from M theory. Okay, yeah, that's what I'm saying, yes. Right, I think it would, yeah, yeah. Of M theory? Yeah, well, I think it requires more detailed study of this compactification onto symmetry theory, okay? One thing that maybe I was fast, but topological term in M theory, right? Beautifully reduces to this new topological anomaly terms, right? That involve both interplay of bulk, one form symmetry, and the boundary one, which is sort of new phenomenon in this context. So we are getting more really than just conditions of particular field that source the symmetry so far. Yeah, but requires, includes all flavor parts as well, and it requires, this is very hard. That's why Ron is involved, because to quantify this, because it's really, those are horrible spaces full of singularities. We excise them. We try to see how to, are there, you know, are there Stokes theorem? How would we study that? And math is not served to us right away. It's really something to explore in more details. Okay. Sorry, is there what theory? Higher cobordism. Yeah, well, maybe some of the stuff could be reinterpreted in that way, but I don't have a good thought on that. Jonathan? Okay. Okay.